Hello, everyone. Welcome to General Chemistry 1. In this video, I would like to summarize the key concept for you for Chapter 10, which is the solid, liquid, and solid and phase changes. Okay, we're not going to talk about the band theory in these chapters. And then the next chapter, 11, we'll be talking about solutions. Okay, but we'll get there. So here, this is just a summary of the big picture, what we need to know. First of all, intermolecular force. Okay, intermolecular force is the force that hold molecules together. So they stay together. Okay. The reason why we need to know this force is the greater these forces, the higher the melting point, and um, in general also the higher the boiling points. That's simply because the stronger the force, the more tightly the molecules are held together. Therefore, it takes more energy to boil them off or to melt them, which turn into higher temperature. Okay, there are 7 different types of intermolecular forces, in which 4 are the most popular. The first one is known as Coulombic attraction force. We also call them ionic force. The second one is hydrogen bonding. Even though it say bonding, it's actually a force. Okay, and it's so good and strong that we call it hydrogen bonding. The last two that's important, the most popular, are the dipole-dipole and the London force, also known as dispersions. All right. Now, let me go back a little bit. Coulombic attraction or ionic intermolecular force is the force present in ionic compound, such as sodium chloride, magnesium sulfate, anything that's ionic. Now, the hydrogen bondings is the force that exists in compounds such as water, amines, or HF. Okay, so any compound that has nitrogen and hydrogen, NH, and OH and HF. So you notice it's called hydrogen bonding because it has hydrogens. And the 3 important atoms are nitrogen, oxygens, and fluorines. So those are the important ones as well. Only those 3, and hydrogens. Okay. Now, don't be confused with sodium hydroxide. Okay, you have sodium hydroxide, that's NaOH, that's it has OH, but it's an ionic compound. So Na plus OH minus, so that's fall into the Coulombic or ionic intermolecular force. Okay. The now when you look at the when you use intermolecular force to compare the boiling point. Now, what if they have the same kinds of force? The 2 molecules or 2 compounds have the same kinds of intermolecular forces. Then what is the next one? We'll look at the molecular weight. Okay, so the higher the molecular weight, the higher the boiling point. If the 2 compounds have the same intermolecular force, we can have example down here. And then also we need to consider the packing ability, which means the shape of the molecules. Okay, and for example here, I give 3 examples. Hydrocarbons, you have a straight chain, you have a little branching, more branching, and more branching. Okay, bulkier, that's what we call them. Now, you can see the more organized or easy to pack, okay, the higher the boiling point, because they stack on each other very well. Okay, so that means the interaction is stronger, therefore the boiling point is higher. Okay, a little bit of branching is not bad. Okay, the boiling point is the same, but more branching and bigger branch reduce the boiling point because they take up too much gaps. Therefore, the interaction between molecules. I mean, they're all the same kind. They're all dispersion. All these compounds are nonpolar. The uh, the same kinds of force, but the effectiveness is not the same. Okay, so this bulky with lots of branches, they don't pack really well. They don't interact really well. So even though the same kind of force compared to the first one, but it's not that effective. So the overall, the net force is not that great. So it's lower. Therefore, the boiling point is lower. Okay. So that's the first topic, intermolecular forces. So be able to identify the type of intermolecular force in a given compound. And to do that, you need to know the polarity. If the compound is ionic, then this is the first one we call ionic or coulombic. If the compound is special, like water, it has OH, NH, and HF, then it's hydrogen bonding. Like alcohol, water, those hydrogen bonding. And if a compound is polar, we call them dipole-dipole. Okay, and finally, if its compound is non-polar, like this guy right here, we call the force is London force or dispersions. Okay, so that's the key concept there. Now the next topic is energy of phase changes. First, let's define the two important parameters here. The first one is the delta H of fusions. That is called enthalpy of fusions, and that's the amount of heat needed to completely melt 1 mole of a substance. Now, if you're given grams of a substance or a compound, you have to convert it to moles. But delta H of fusions also come in joule per grams. Per mole, it comes in kilojoule per mole, and it's also comes in as a unit of joule per gram. So that will be convenient if you have the mass in grams. Okay, you just have to multiply them together to get the energy, but it's in joule. So pay attention to the units. That's my point. Okay, and we can do anything. We can convert gram to mole. We can leave it as gram. Depends on what the units of delta H given. All right. Similarly, we have delta H of vaporization, which is the enthalpy of vaporizations, is the amount of heat needed to completely vaporize 1 mole of a substance, or 1 gram. Okay, so we can have a phase diagram. Okay, phase change diagram, going from really cold solid to hot vapors. And that's, believe it or not, that would take 5 steps. And here's the summary of the 5 steps. The between phase changes, we do the MC delta T, and there's 2 paths. That's fusion, which is the melting, and vaporizations. Those are the ones that we don't use temperature change, because there's no temperature change at all. Okay, and then if we ask to figure out the total energy, then remember it's cumulative, so we have to add them all up together. Okay, so I split them up into 5 steps here for you, Q1 to Q5, and the formula Q1 is MC delta T, and C, notice that's the CS right here, and I define it as specific heat for solid, such as ice, and delta T is the temperature change in step 1. Now, step 2, notice that there's no temperature change. That's the melting process. During the melting or the fusions, there's no temperature change. For water, water melts at 0 degrees Celsius, and when ice start to melt, it's at 0, and when it's completely melt, it's also 0. And then after that, when it become 100% liquid, then it's heat up. Okay. All right. So after it's melting, after the fusion, you see it becomes Cl, because that's liquid. It becomes liquid. So we have to use different C value. Okay. So this C will be given. Okay. Delta T we can calculate. Mass will be given. And then next, heat of vaporizations, and then you have heat of heating up, which is at that point water's already turned into vapor, which is a gas. Okay, so there's value for those right here. For water, okay, for each compound there's specific value. Okay, of course. CS, which is ice, is 2.03 joule per gram degree Kelvin. Now, degree Kelvin or degree Celsius, when you do per degree, it's the same because when you do the subtractions, they come out the same. Okay, the 273 doesn't come in because they already cancel out. For liquid water is 4.184, and that's the one we use all the time. Okay, ice is rarely we use that. Okay, vapor C is 2.09. Okay, and fusions is and here's, as I mentioned before, is per gram, so 334 joule per gram. And then for vaporization, it takes more energy to make the molecule fly, so that's 2260. So it's a lot more energy to vaporize something. Okay, and that's joule per 2260 joule per gram. And remember, joule per gram per Kelvin is the same as joule per gram per Celsius. Per degree is the same. Doesn't matter what kind of degree. Okay. The heat of fusion, as I mentioned before, sometimes given in kilojoule per mole, and in that case, the amount of substance must be in mole, and make sure the units matches all the units. Okay, so here's the example of the heating curve, and as I mentioned before, you got 5 steps. This is temperature. Temperature increase from low to high, and then this is the reaction or the progress of the melting and so on and so forth. Now you start out with really cold. For example, in this case, start out with -30, and the next critical important temperature will be 0. Okay, so there's only 2 important temperature of water: 0, which is the melting point, and 100 degrees Celsius. That's the boiling point. We talk about at normal pressure, 1 atm. Okay. So you got 5 steps there: Q1, Q2, which is the fusions, Q3, heating up to 100, and then 100 when it starts to boil, that's vaporization, which is Q4, and then the Q5, heat up to hot vapors. Okay, in another video, we'll look at this in detail. Okay, so we'll look at, we'll do the calculations. In this case, this practice problem, you can see delta H vap of water is given in kilojoule per mole, and it's at 25. This is active evaporation. So of course, regular evaporation of water is at 100 degrees Celsius. But this is on our skin, our body, so it cannot be 100 degrees Celsius. That would be too hot. So it's called active evaporation, and that's our body initiate, our body can facilitate it, and that's energy is 44 kilojoule per mole. Okay, it takes more energy. And in that case, it's very simple. You don't need the temperature for the calculation. You just need 1.5 gram, convert it, and that's mainly water, convert it to moles. So you take the 1.5 gram divided by molar mass of water, which is 18.02, you get number of moles. And then you turn around, multiply it by the heat of evaporations, here given 44.0 kilojoule per mole, and you should get the answer. Okay, should be 3.66 or something like that. All right, so give that a try. All right, so that's phase diagram and heat calculation. So don't forget those 5 formula important, and depends on the step, use the formula correctly. Okay. The 2 flat ones, so those are the ones that you don't have delta T. Notice that. One is the fusion, and the other one is the vaporizations. Okay, the next concept is called phase diagram. Again, back to the phases of matters. There are 3 different phases. Water and CO2s are the 2 most popular compounds on Earth. So here, that's why I include them here. There are 3 different phases, as I mentioned: solid, gas, and liquid, or solid, liquid, and gas. Notice the pressure. The higher the pressure, the more tendency to be a solid. And the higher the temperature, the more tendency for a substance to be a gas. In the middle will be a liquid. Okay. Now, usually a gas has to turn into a liquid before it turns into solid, or the other way. Okay, solid has to melt and then turn into a gas. But it's possible to go directly from solid to gas or gas to solid. Okay, anything's possible here. Now, notice there's two important points here. One is called a triple point. That's when you have all three phases coexist. And that would be at T3, we call that T3 and P3. So it has to be specific temperature and pressure. Well, P for CO2 is about 5.1 and temperature is about negative 56.6 degrees Celsius. when you get that combination of pressure and temperature, you get all three phases. Solid, liquid, and gas, CO2, exist at the same time. Now, if you have higher pressure, it's going to turn into a solid. If you have lower pressure, it turns into a gas. And you change both temperature and pressure if you go that way. So if you increase the pressure, you also increase the temperature. Notice that it's going to turn into a liquid. You guys see it? Liquid CO2. Okay. That's, I believe they call critical fluid. Okay. Liquid CO2 is very useful for extraction of compound like caffeine, things like that, nonpolar compounds, because CO2 is nonpolar. Now, the other important point is called TC, which is the critical point. And of course, every single point you have two values. At that point is 31 degrees Celsius. That is critical at 72.8. Okay. Now, beyond that, so what do you call critical temperature, right? Beyond that point, okay? Beyond that, if you go beyond that temperature, like 32 degrees Celsius, it has to be a gas. Okay, so beyond that, the gas phase take over. Even though the graph, that's why the graph end, the graph ends right there. Okay, beyond that, it's too hot for CO2 to be a liquid. Okay, doesn't matter what pressure you apply, it's always going to be a gas beyond 31 degrees Celsius. That's what it means. It has to be a gas. Okay, so that's called critical. So molecules have too much energy. They cannot be compressed. They cannot be close enough to be a liquid. So in liquid, the molecules are closer together than in gas. Now, for water, it's different. Notice the slope of this line is negative slope. For water, the triple point, we need to look it up. Okay, here it doesn't show, but I know the triple point of water is low, of course, close to melting point. And when you have three phases coexist, which is liquid, gas, and solid, liquid, and gas. Now, the critical temperature here, I don't have that value, but we'll look it up. I believe it's really hot. It's over 300 Celsius or something. Okay, but again, we'll look it up. Which beyond that critical temperature of water is a vapor. It's hot vapor, and cannot be condensed into a liquid. Okay, so we'll look up that critical temperature of water. That'll be interesting. Okay, that's the second important one. A couple more things, and that will wrap up these chapters. Vapor pressure. The vapor pressure is the pressure of the vapor that come off the liquid, and so when it reaches the equilibrium point, and that's create a vapor pressure. So at any moment you look, there's always molecules that take off the liquid phase and then come back and forth. And when it's in equilibrium, you can figure out that vapor pressure. So, and that depends on the temperature, right? The hotter the temperature, the more vapors in the air. Now, so we call that a PVAP T1 and pVAP T2, or we can just call P1 over P2. Okay, so if you take the natural log of P1, which is as T1 over P2, that will be the same as, that will be equal to delta H of vaporizations divided by R. And remember, R here is 8.3145 joule per mole Kelvin. So don't forget to convert delta H to joule. Okay, that way match with the units of R divided by R, and then 1 over T2 minus 1 over T1. All right, so if you know vapor pressure at T1, you can figure out vapor pressure at T2, and that's the whole point, okay, of these formulas. When you change the temperature, you can figure out, it's like a gas law basically. When you change the temperature, you can figure out a new pressure. So except the formula here is vapor pressure. It's more complicated. It's a lot of math involved here. And here's an example. And don't forget to convert temperature to Kelvin. We can leave the pressure in torrs as long as it's consistent. P1 and P2, the same units. That'll be fine. Okay. So give it a try. And finally, there's the last topic here is the unit cell geometry. And there's many different geometry, but here I only put one, which is the phase center qubit. So if you chop off a cube, okay, and you got a repeating unit in here, repeating unit. If you chop off one piece and you look at the atoms, okay, and the next one's going to be the same as this. They're all connected together. So you got a corner, 1/8 of an atom's there. The and that's half. Okay, so it's half of an atom, you can divide it by 4, and that's a piece right there. So that's why it's 1/8. Okay, it's 1/4 and then divided by 2 because this is only half. So that's why it's 1/8. Okay, so if you know the radius, okay, if you know the length of the cube, when you chop it up, when you look at it under X-ray or something, when you look at the unit, the length of the cell, you know the length of the cell, which is the D, you can figure out R. Okay, because by doing the math, Pythagorean theory or something, right triangle, you do all that and you figure out the radius is going to be the length of the H divided by square root of 8. Or if you know the radius of the atoms, you can figure out the length of the H. Okay, so, but the purpose is to figure out either D or R, if we know one. All right. So, and here's a few practice questions for us to do. All right, so in the next video, we'll do chapter 10, which is solutions, review of solution concentrations, and some calculations. Okay, thank you for watching.